Let's talk about confidence intervals. Before we start confidence intervals, there's some skills you're going to need. You should be comfortable with probability, the z-table, and maybe most important of all, sampling distributions. Hi guys, we're going to talk about confidence intervals for the population mean this time, not the population proportion. So this is a new video, even though I reused my whole introduction. That's because it all still applies, and it saves me a couple of minutes in this particular situation. So before we do that, though, we're going to talk about the exercises that I proposed to you at the end of confidence intervals for the population proportion. We're going to do that right now. So the first one was a confidence interval where I think I was asking you for a 90% confidence interval, but I proposed that our p hat, our sample proportion, was 0.78, and we were working with a sample size of 40. I also cautioned you to check out to make sure that you have normality before you start. And that's really what this first one was about. I have a feeling maybe some of you guys already guessed that. If you check NP, we have 40 times 0.78. And that comes out to, what is it, 31.2. So we're okay in that respect. NP is certainly equal to or greater than 10. But the problem is this. If we check n times 1 minus p, we have 40 times 1 minus 0.78, which is 0.22, and that comes out to only 8.8. So we do not have normality, and in this situation, we just hit the brakes. We just stop. We can't do a confidence interval utilizing the methods that we learned in confidence intervals for a population proportion parts 1 and 2, the previous video. So it just flat won't work. So we just put on the brakes and stop. For the second one, p hat was 0.48 and our sample size was 200. So it looks like we're probably in pretty good shape here. We're still gonna check. NP is 200 times 0.48. And that comes out to 96, so that's okay. That's equal to or greater than 10. N times 1 minus p is equal to 200 times 1 minus 0.48, which is 0.52. That's a 5, in case you're wondering. And for that, we get 104. If you're saying to yourself, wait a second, don't NP and n times 1 minus p both sum to n? Yeah, you're exactly right. So once we got 96, if you're a little insightful and a little careful, you can say 200 minus 96 is certainly greater than 10, so I can proceed forward. As long as you're careful. I'm not really into the shortcuts, but you can do that, and that's actually okay. So we'll move forward to doing the confidence interval because we have normality. So we were asked for a 90%, I asked for a 90% confidence interval here. For 90%, using the z-table, you're going to have 1.645. In other words, you can use 1.64 or 1.65, generally depending on the class or the scenario or the lab or whatever that you're working with. You'll get a direction with regard to that. 1.65 among the two would be a little more conservative because it'll result in a slightly wider confidence interval. And that means that you're more likely to capture the true population proportion. So it's a little bit more careful to round up or to use 1.65 if you're going to use either one of the two. Even so, as I've mentioned in previous videos, I like to use 1.645 and split the difference. It feels accurate to me to do that. So I do. I calculated the standard error. I'm not going to do that for you in front of you. I think you're in a spot where you can probably do that and just check your work against mine. I got 0.035327, and that resulted in a confidence interval of 0.421887 and 0.538113. So make sure that you got the same thing as me. Let's do the next one. For the next one, our p hat, our sample proportion was 0.71, and the sample size was 400. So we have a relatively generous sample size compared to the other problems. If you work out NP and n times 1 minus p, you'll get 284, which is actually 4 times 71 if you think about it, and n times 1 minus p, which is 400 minus 284. You can do the math on your own, but you're going to get 116, unless I'm completely confused. And that happens. But I don't think in this case. So we have normality. Our standard error is 0.02268, and that lends us a confidence interval of 0.665531 to 0.754469. So something I didn't do with the last confidence intervals. Let's just remind ourselves exactly what we're talking about. Oh, by the way, I left something out initially. I should have reminded you that we're going for a 95% confidence interval in this case, aren't we? So that's 95%. So instead of using 1.645, look it up on your table. You're going to use 1.96. So our confidence interval going from this number to this number says that we are 95% confident. And by the way, even for you math majors out there, in many scenarios, academic scenarios and other scenarios, it's appropriate or possibly more appropriate to answer a question like this verbally, either verbally speaking or written, writing a sentence something like what I'm about to say. We're 95% confident that the true population proportion would be between 66.5531% and 75.4469%. That is an entirely appropriate and rigorous way to present the answer, especially since I use the word confident, not probability. We really say it's a confidence interval. Here's our fourth practice problem. We have p hat equaling 0.04. Our sample size is 250. And I asked for a 99% confidence interval. So if you work out NP and n times 1 minus p, you'll find that we do meet the requirements. NP is actually equal to 10 in this case. N times 1 minus p is equal to 250 minus 10. Work it out. It actually comes out to 240. You'll see that that's the case. So we have normality. So now we have to calculate the standard error. Again, I'm not going to do it right in front of you. I want you to do it on your own and then check your work relative to mine. I got 0.012394, if I remember right. I'm checking my notes. And that is what I got. And our confidence interval would be 0.008087 on the left and 0.00719113. So we are 99% confident that the true population proportion would be between 0.8 of 1% and 7.19%. That's the result of that calculation. So let's talk about confidence intervals for the population mean. If you've been following the videos for confidence intervals for the population proportion, then you, thankfully, basically have the idea, okay? Instead of having p hat that acts as our pivot number that we're adding and subtracting to and from, we actually have a sample mean, because remember, this is basically the same idea, but instead of taking however many multitudes of sample in our minds, all these samples, and getting the sample proportion, instead of that, rather, let me phrase this clearly if I can, we are using the sampling distribution of the sample mean, and that means we're envisioning ourselves taking all possible samples and taking the mean from the samples and utilizing that as the basis for a sampling distribution. Now we move one further step, and we're doing confidence intervals utilizing that idea. So we are basing this on sample means. From a student's perspective, you should be getting a little blinking red light or an exclamation point in your head right now that says, oh, that's how I can tell the difference between the questions. If you're given a sample and the mean to that sample, you're going to be doing a confidence interval for the population mean. You're not going to be doing a population proportion when the sample yields to you a mean. Likewise, if you're doing a problem, this is kind of like a keyword type of thing. If you're doing a problem and you're given the sample proportion, stop what you're doing. You're not doing a question that has to do with the population mean. Rather, if you have that, you're doing a question involving the population proportion. So we did that already, so I'm not going to go over that again. Right now we're doing confidence intervals for the population mean. So you're going to take, in doing this, you're going to take your sample mean and you're going to add and subtract the appropriate number of z's based on the confidence level you want. For example, our default value is 95%, and in that case you're going to use 1.96. You can add and subtract the appropriate z for your confidence level. I like to label it z star, times another star, but this time it's multiplication, the standard error. Remember that we have a new, or rather I should say different, standard error formula in the case of confidence intervals for the population mean. We're talking about using something which references the sampling distribution of the sample mean. So there's our formula. Let's get a little bit more specific about that. Here's a more specific example. Let's say that we have a sample that we've taken, a sample with a mean of 27, and our sample size was 36. That makes it easy. You can probably see why. And we're doing this within a population whose standard deviation, that sigma, is 6. A couple of things you should note. That's Greek letter sigma, assuming I wrote it legibly. That means that we are obligated to understand that that is the population standard deviation. If I had been talking about the sample standard deviation, I would have written S equals something. And it might very well have been a different number. The sample's standard deviation, the standard deviation within this sample, is probably close to that, but somewhat different. We're going to talk about that after this example. What I want you to do right now is to recognize, oh, that was Greek letter sigma. I'm getting the parent population standard deviation, so we can proceed that way. So our sample size is greater than 30, so we know we have normality. I'm all set. We can proceed. Let's go with 95% confidence because I don't have the energy to think of something else different right now. And it is the default after all, so we'll go with that. So I'm going to do a confidence interval. I'm going to take x bar and both add and subtract 1.96, because that's the z value necessary for 95% confidence. Look it up on your table periodically and remind yourself why. 1.96 is the z value, which leaves you a tail of 2.5% on the right and a tail of 2.5% on the left. If you go to the left, negative 1.96. So being that we have 2.5% in the two tails, that gives us a total tail area of 5% or 95% in the center, just so that we can remind ourselves where that comes from. So I have 1.96 standard errors times the standard error. I have 1.96 multiplying the standard error. Well, the standard error is going to be the standard deviation of the population divided by the sample size, which is 6 over 6, or 1. So I have 1.96 for 95% multiplying my standard error, and that's what I'm adding. And that is also what I am subtracting. So I do that, I generate two numbers, and I'm going to get, unless I'm totally nuts right now, sort of doing this on the fly as I roll video. I should have done this ahead of time. 25.04 on the left, 28.96 on the right. So our confidence interval statement would be, we are 95% confident that the true population mean, mu, would be between 25.04 and 28.96. That would be the answer that we're giving. Here's the issue, and this is, because this is so similar to what we've already learned in the other videos for confidence intervals, I'm going to give you some review questions at the end of this video, but I am not going to actually talk more about this part of confidence intervals for the population mean right now, because I think you can get it as long as you have the basic formula, which I gave to you just a few minutes ago. Here's what I really want to talk about. If you need to take a sample from the population, it's very likely that you don't know a lot about that population. So what's the likelihood that you're going to have sigma? Not always super high. You may not have it, and in those cases, you are forced to substitute the sample's standard deviation. So let's talk about what you do in that situation. So let's imagine a situation, and this is very common, when you don't have access to the population standard deviation, and you're forced instead to substitute the sample's own standard deviation. That's going to create a certain additional uncertainty in the answer that you get. Like, for example, our confidence interval just now, I won't rewrite the values because you just had it there, and you can put that in your notes if you want. Our confidence interval went from 25.04 on the left to 28.96 on the right. And we were able to have 95% confidence in that interval. If there were some element contributing to our uncertainty, we would be forced to widen that a little bit in order to maintain the same level of confidence. That makes sense. It's a little bit easier to hit. You're shooting your bow and arrow. It's a little bit easier to hit a bigger target. So if somebody moves the target further away from you, that's going to reduce your confidence. So how do you regain your confidence in your ability to hit it? You get a slightly bigger target. And this is the same idea. What we need is a situation where when its uncertainty is increased, like for example, the substitution of the sample's standard deviation rather than the population's standard deviation, what we're going to do is take our confidence interval and just buff it out a little bit, knock it out, make it a little bit wider in order to maintain whatever level of confidence that we want. So I'm actually talking about a cousin of the normal distribution that we've talked about so many times, the z distribution. And this sort of closely related curve is called the t distribution or t curve. And you look up values for it on a t table. It's all using lowercase t. You're going to look up those values on a t table. And this is a curve that is very closely related to the normal distribution. It's just that, just as I've been describing, it's just widened just a little bit to compensate for certain causes of additional uncertainty. So that if you have certain things going on, like the necessity to substitute the sample standard deviation rather than the populations, you have a little additional uncertainty. You refer to the t-table instead of the normal distribution table, and you can still get 95% confidence in your answer. There are two circumstances under which a person has to utilize the t-distribution rather than the normal distribution. I'm going to lay those out for you. So if either of these two circumstances that I'm about to write apply, you stop using the z-table, the normal distribution table, and you use the t-table instead, okay? So first, if sigma is not known, you can go ahead and use the t-table. You're just going to use S instead. So you need access to either the population standard deviation or the sample standard deviation, really to do this in a fairly, let's call it, watertight manner, in a fairly rigorous manner. The first circumstance is if the population standard deviation is not known, you can go ahead and use the t-table as long as you use S instead. I want to mention that there are schemes for estimating these things. Like, for example, it's sometimes permissible when you're only after a super rough estimate to take your range and divide by 4. And you're going to actually get kind of a sort of a rough estimate of a standard deviation that you can use. But this is obviously really rough and made really inaccurate when you suffer from extreme values or funnily shaped distributions and so on. So this is just a really crude and broad form of estimation if you want to do back of the envelope type calculations. Generally, we go by these rules. We like the population standard deviation, and if it's not available, we use S instead and substitute the t distribution for the normal distribution. Here's the second circumstance. If our sample size is actually less than 30, then we can also proceed under those circumstances too. But when your sample size is less than 30, it's really a little bit too small to use the normal distribution table. In fact, you can't. So what we do is we use the t-table under those circumstances too. It's just that we no longer can rely on the sample size to assure us of the normal shape of the sampling distribution that we're sort of relying on as fundamental to the confidence interval we're doing. So since we can't rely on a normal distribution for our sampling distribution anymore, we just need to know from some other method that the population is normally distributed. From the student's perspective, you're just going to be looking for, in the question, does it say the population is normally distributed? If it does, you can proceed that way. If you're a statistician, there's other ways of determining with a certain, again, level of confidence whether or not the population is normally distributed or close enough for you to be able to do a confidence interval with a sample size of less than 30. So let me just sum this up to make sure it's clear. If you're going to do a confidence interval for the population mean, when one of these two circumstances applies, or both, you go from normally using the normal distribution table to using the t-distribution table instead to compensate for the additional uncertainty that each one of these two circumstances, or having both of them, would introduce. Let's talk about the t-table and reading the t-table. By the way, my audio is already not awesome. I think in previous videos you may have heard the train, which is going past right now. I'm right outside my window. The neighbor's baby, kind of a charming sound. And right now they're screaming and yelling and leaning out the windows right now because it's just after 7, banging pots and pans for healthcare workers. So that's awesome, but I'm trying not to be too crude with these videos, and they're kind of messing me up. But I don't have much time, so I'm going to proceed anyway. So if you hear something, that's what it is. Okay, the t-table. Let's figure out how to read the t-table. So if you're looking at the t-table in a textbook or something like that, or online, there's a couple of different ways they're configured. But they always have the same elements. They just might be arranged differently. One thing about the t-table that's, in fact, I have to say really the only substantial thing that's different about the t-table versus the z-table is that when you're reading the t-table, you need to know what's your df. That stands for degrees of freedom. Okay, degrees of freedom is a discussion all on its own. I like doing this. I may continue doing videos even after this semester. One of these days I'm going to devote a video to degrees of freedom and what the heck is that? Generally, students in an undergraduate level it's very common for them never really to be taught the reason for that. So we're not going to go into that right now, but you need to know what your degrees of freedom are. And previously I was talking about, in the last example, a sample size of 36. So in that previous example, if I did not have the population standard deviation sigma, and instead I had S, the sample standard deviation, whatever it might be, I would say to myself, oops, I have one of those circumstances in which I have to utilize the t-table instead of the z-table. So, gee, I got to figure out what my degrees of freedom would be. And degrees of freedom is always, in the case of using the t-table, n minus 1. So you're not going to find many calculations easier than that in statistics. That's a pretty easy one. Maybe mu sub x bar equaling mu. That might be easier, but that's pretty easy. So in this particular case, my degrees of freedom are 36 minus 1, which is 35. So we know that our degrees of freedom equal 35. I'm going to write out sort of a mini version of a t-table right here to give you an idea of how to read it. So on a t-table, if you take a look at a t-table, it's very common. There's different ways that these are configured. And towards the end of this, I'm going to draw a picture to show you the area of the t-curve, which looks just like a normal curve. What area of that t-curve we're being given values for. But I want to start you off by learning how to read it and seeing what's different about it. One very common way for these tables to be laid out is to have degrees of freedom written on the left, and then the left-hand column is a row of potential degrees of freedom. And it's really common. If you look it up on the internet or you look in different textbooks, you'll find variations. And so that's why I keep qualifying myself by saying it's very common so it's very common to have degrees of freedom 1, 2, 3, all the way through, let's say, 29 and then 30. And then you'll notice that the table will start skipping 30 to 40 to 60, very often to 120, sometimes to 200, to 500, straight to infinity. I'm going to explain why that is in a moment. Let's just for now concentrate on taking care of the problem we're doing. So we have degrees of freedom 35. So what would we do in this particular case? We would have to read the table and figure out where to go from here. There's a few strategies. 35 doesn't appear here. If you go to the lower degrees of freedom, instead of 40, you go with 30. You're doing something slightly more conservative, because the lower your degrees of freedom, the wider the resulting distribution. And anytime you go wider, you are preserving confidence. So if you want to do the conservative thing, go to the next smaller degrees of freedom. A second strategy is for people to sort of average. There's a form of finding differences in between called interpolation, which can work very well. For example, if our degrees of freedom was 31, then we would take values that were 1/10 of the distance between these two values. I wouldn't ask my students to do that, but that's a second strategy. A third way for this to be handled in, scholastic settings, school settings, is for a given instructor just to say, use either one. And that's actually my strategy too, because at this point, just learning to do confidence intervals is usually my priority. So I'll usually tell my students that they can use either one. If you round down, you're going to have a slightly more conservative, more confidence-inspiring confidence interval that's going to be a little bit less precise. If you go up to the next higher number, you're going to find something a little bit narrower, so it's going to be more precise, but you've actually lost an ever so slight amount of confidence. So for my students, for example, I always tell them, for now, use either one, and I'll leave it later in their statistics program another semester or something like that to say, well, wait a second, let's take a close look at what we are really doing. And in fact, when you start doing these problems, in a setting where they are not the focus, like you're doing political polling or you're doing some kind of research in the natural sciences, you're going to use software and you can punch in your sample size and it'll find you an exact value for exactly 35 degrees of freedom. So it ends up being an academic question anyway. Now the particular t-table that I'm talking about has a diagram at the top that looks like this. You have a curve that looks like a normal distribution curve, and it'll be marked at the edges with something that says t critical value. I'm going to put t crit as an abbreviation. And on the left, negative t critical value, again abbreviated t crit. And then it's going to have the middle shaded. So this is the perfect table to use if you're doing a confidence interval, because you're being given a completely symmetrical area in the middle, and it's giving you immediately the t critical value that you're going to need, the negative and positive version of which, to get your confidence interval. So it's kind of a shortcut. That's what this table would give us. So here's a t-table with degrees of freedom on the left, going from 1, 2, 3 through 29 and 30, then 40, then 60, then higher numbers. And then, in the case of this particular type of t-table, and then actually confidence levels across the top, starting from 80 in this case to 0.999, 99.9% confidence. And somewhere towards the middle, you're going to find our favorite value, 95%. And below those confidence values, 80, 90, 95, and so on, all the way through 0.999, you're going to find values. I've written in a few of them here. And that's actually the t critical value that you're going to need to get that level of confidence. That's completely equivalent to the z value that you've gotten used to using, hopefully so far. You'll notice that by the time we get down, if you look at the table carefully, you'll notice that by the time we get down to 30 and 40, they're very close together. That's an example of why they start skipping values, because they actually stop differing that much. You'll see a little bit more of a difference over here on the right side. At 0.999 confidence, between 30 and 40 degrees of freedom, it does change by a tenth. It goes from 3.65 down to 3.55, which is some change. Over here it's changing by 100th, here it's changing by a tenth, but it's still not that much. Underneath 0.95% confidence, we have 2.04 and 2.02. Okay, again, really close together. By the way, it's probably a good idea for you to notice that these are really close to the z value of 1.96 for 95% confidence. The further up you go up in the table, and I would encourage you to check it out and take a look, you're going to start seeing values that go to really kind of wacky places. I'm looking over my shoulder because I'm noticing that if I'm reading it right while I'm talking to you, at 2 degrees of freedom, 95% confidence, we have 4.3, and at 1 degree of freedom, which you're never really going to do, unless you're forced to by circumstance, you're not really going to do a test with a sample size at 2. But the math exists to allow you to do it. It's just that the t-value would be so high, you're probably not going to be able to come up with really useful results. You'd also run into trouble in another area of statistics called power. Your statement of confidence would lack something called statistical power, which I would encourage you to go and Google or something to look up if you want, but it really would probably not be that useful. But the math exists to support it. With a sample size of 30 or 40, though, or 36, we can do some pretty sound confidence intervals, and that is the t-critical value that we would use. Go ahead and take a look at your table and make sure that you see the same thing. That's the t-critical value that would be required for us to get 95% in the middle of a t-curve when we have between 30 and 40 degrees of freedom. Sample sizes of between 31 and 41, in other words. So let's imagine that we're doing another sort of sample, and we're going for the sample mean. Let's say our sample size is again 36, like it just was, so our degrees of freedom are again 35. We get a sample mean of 28.7. And we want 95% confidence. And our sample has a standard deviation of 5.8. Okay, now look. We might be getting this sample from the population that I just discussed. But samples differ. In the case where you're working with a situation like this, you have only what the sample gives you. But it's enough to get good work done. We're going to proceed with the t-statistic. If I look up on the table, as if I'm looking it up fresh right now, I notice that with the degrees of freedom of n-1, 35, for 95% confidence, I notice that I'm using 2.04 or 2.02. I'm going to go ahead and use 2.4 as my t-critical value. So that's 2.04, because I want to be conservative about it. And I'm going to be utilizing that, as I did with the z-value, to multiply the standard error that I get now. I have to calculate the standard error using s instead of sigma. So let's go ahead and do that. And after I do that, I'm going to add and subtract my sample mean to and from this. The standard error. Let me make a quick note, by the way. I just realized I may have done something that might confuse somebody. I wrote S sub x bar, and you really ought not to be confused by that. That's the same thing as sigma sub x bar, except when you're utilizing the sample standard deviation because you don't have access to the population standard deviation. So in previous videos, like for the sampling distribution, I would have written sigma sub x bar. In this case, I wrote S sub x bar because we're utilizing that, the sample standard deviation, to come up with our standard error. In this case, I got the standard error equals 0.96, and then 6 is repeating forever. I'm going to round it to 0.967. And that's what we're going to utilize. Let me go ahead and clear the board, and we're going to go ahead and calculate what that confidence interval is. For the right-hand side of the interval, I got 28.7 sample mean plus the t-critical value, 2.04 times 0.967. That's my rounded standard error, and that would equal 30.673. That's also rounded. That's the right-hand side of my confidence interval. For the left-hand side of the confidence interval, the mean minus the t-critical value times the standard error, I got 26.727. So there's our two values. We can say that even though we didn't have access to the population standard deviation, that with 95% confidence, we can say that we are that confident that the true population mean would be found between 26.727 and 30.673. So we maintain our level of confidence even though we are not in the optimum position with regard to population standard deviation. We have only the sample standard deviation. So since this is really the same thing, or so similar to doing confidence intervals with the population mean, with the z-table, and actually pretty similar still to doing confidence intervals for the population proportion, I'm really going to give you some practice problems right now, but they are just looking up values on the t-table so that you can make sure that you understand how to look up those values. Let's try these. Let's propose a situation where your sample size was 27 and you're looking for a 98% level of confidence. Please remember that if your sample size is less than 30, you still need to have some other alternative way of assuring yourself that the population distribution is normal, because your sample size doesn't do that for you anymore. So you'd have to have, again, from the student's perspective, you'd have to have a test question that said, the population is normally distributed or something along those lines to proceed. Same thing over here. So you may or may not have the population standard deviation in either of these two cases. But because the sample size is less than 30, you'd still need to use the t-table, and you'd still need an outside assurance of normality. So we'll go ahead and we'll place the values for those over here on the right. I'm going to explain all of these questions first, and then I'll have you pause the video, and then I'll fill in those values, and we'll make sure that we agree. The third one, we have a sample size greater than 30, so we're okay. We have normality based on that. We don't care if the population is normally distributed. That's a good thing. And in this case, we're looking for a 99% level of confidence. Okay? Go ahead and pause your video now, and we'll come back. Okay, so here's what we're looking at. With a sample size of 27, our degrees of freedom would be 26. And for 98% confidence, I read from the table a t-critical value of 2.48. For 13 degrees of freedom and 90% confidence, 1.77. And then finally, for 61 degrees of freedom and 99% confidence, I read 2.66. Now, you probably noticed, if you looked at the table, that there is no 61 degrees of freedom. But here was a real clear case of, let me round down and go with 60 degrees of freedom. And that's how I got that value. That is acceptable when you're using t-tables from a table. Again, in reality, moving forward, when you're actually doing work with this stuff, you're going to use software anyway. And software can, for like exotic reasons for parts of math that we're not talking about in this video, you can look up degrees of freedom that are not integers, not integer values. Software can do a lot of amazing stuff. So you're basically going to be relying on that. But in this particular case, we would read 2.66 off the table. The last thing that you probably noticed, if you read the table and you go all the way down for degrees of freedom, you're going to notice that there's an infinity row. Take a look at that infinity row. As your sample size increases, so that your sample size is so big that it's infinity, or certainly a very large number. If your sample size is in the thousands, this would apply pretty much also in a day-to-day, real-life, functional way. You're going to find that the critical values you read from the t-table are actually the z-values. Because as your sample size gets bigger, the t-table, it's said to converge on the z-curve, on the normal curve. So once you're dealing with samples of, in the thousands, big samples, it's no longer an important difference anymore for most work. It's a moot point. Okay, guys, thank you very much. Go ahead and comment on the bottom, and we'll see you soon.